Imagine a collision 500 million times more powerful than the largest nuclear bomb you've ever seen. That is the very power that tore a 2,500-kilometer wide wound across the face of the moon. And here is the paradox. The largest impact in the solar system hid the greatest secret it should have revealed for decades. This collision was so violent, it should have punched through the moon's 40-kilometer crust like it was paper. Because of that, it should have exposed the planet's heart 13 kilometers deep, the mantle layer. But even our most advanced telescopes in orbit found only more crust. This was physically impossible. Until China's small U-22 rover descended into this colossal pit of hell. But what was truly unsettling was not that we found what we were looking for. It was where we found it. If you love chasing the universe's greatest contradictions, then don't miss this video and don't forget to subscribe, because you are about to see how the impossible became possible. Are you ready? We begin. For years, we thought we knew the moon. That familiar face in the sky had accompanied humanity for thousands of years. All our stories, all our mythologies were written on that face, because that was the only face we could see. But the moon also had a side that remained in darkness, a side that never looks at Earth. And in 1959, when the Soviet spacecraft Luna 3 looked upon that unseen face for the first time, everything changed. Because what we saw was not the moon we knew. The side facing us was filled with vast, dark basaltic plains called Maria. But the far side of the moon was completely different. There were almost no dark spots, only a bright, crater-pocked, ancient landscape stretched out. This asymmetry was shocking. No one could explain the sharp difference between the two faces. Therefore, we had to wait decades for better images. First, the Soviet Zond 3 and Zond 6 probes. Then, in 1968, the crew of Apollo 8 saw that face with their own eyes. Frank Borman, Jim Lovell, and Bill Anders lost all radio contact with Earth in those brief moments they passed behind the moon. It was in that absolute silence that they encountered a landscape no human had ever seen before. It was a geography far more battered, far more rugged than the face that looks at us. But in that landscape, near the South Pole, an unusually large and dark circular shadow drew their attention. We would have to wait until 1994 to understand what that shadow was. Because the Clementine spacecraft, launched that year, mapped the moon's topography with its laser altimeter, and it proved that the shadow was not just a shadow, it was a hole, the deepest, largest hole in the solar system. Because this structure was unlike anything we knew, its name was now the South Pole Aitken Basin, and the numbers are almost impossible to hold in your mind. The basin is approximately 2,500 kilometers wide. That's equivalent to the distance between New York City and Denver. If you stood in the very middle, you would never see the edge. The horizon would simply curve away in every direction, and its depth is a full 13 kilometers. When you consider that the deepest point on our own planet, the Mariana Trench, is about 11 kilometers deep, this is an incredible figure. The moon, with only a quarter of Earth's diameter, bore a scar deeper than the deepest ocean trench on our own planet. But that wasn't the most shocking part. The real question was, what would it take to open a wound this massive? So, scientists returned to their models. The answer was terrifying. The impact that created this basin occurred between 4.2 and 4.3 billion years ago. The object that struck the moon was at least 200 kilometers wide. For comparison, the asteroid that wiped out the dinosaurs and formed the Chicxulub crater was only 10 to 15 kilometers in diameter. This was not a mountain falling from the sky. This was a small world. The energy released in the collision is estimated to be around 10 to the power of 26 joules. This number is far beyond our intuition. But we can make a comparison. The largest nuclear weapon ever detonated on Earth, the Soviet Tsar bomber, released about 2.1 times 10 to the power of 17 joules of energy. This impact was about 500 million times more powerful than that. It melted thousands of cubic kilometers of rock in seconds. This impact should have pierced the moon's crust. According to all models, it should have exposed the mantle beneath the crust, the deep interior of a planet. But there was a problem, because the moon's crustal thickness varies. On the near side, facing us, it averages 30 kilometers, while on the far side, it's 40 kilometers. Beneath this basin, the crust is less than 10 kilometers thin in some places, and some estimates suggest it drops to as low as 5 kilometers. So, the mantle absolutely should have been exposed. The mantle is composed of dense minerals rich in iron and magnesium, like olivine and pyroxene. These are completely different from the lighter minerals like anorthosite that make up the crust. But every single spectrometer looking from orbit, including Clementine, India's Chandrayaan-1, Japan's Kaguya, and NASA's Lunar Reconnaissance Orbiter, found the same thing at the bottom of the basin, just crustal material. Where the mantle should have been, there was only crust. This situation became known as the missing mantle problem. It was one of planetary science's quietest, but most stubborn puzzles. There was a hole deep enough to show the inside of the moon, but that interior was nowhere to be seen. The leading hypothesis was burial. Perhaps after the impact, the floor of the basin was a sea of molten rock. When this sea cooled, it might have covered the exposed mantle with a layer of volcanic rock, effectively sealing it. Subsequent smaller impacts would have pulverized this surface into dust, hiding everything. There was only one way to solve this mystery. Looking from orbit was not enough. It was necessary to land there. To land on the floor of the basin, find a fresh, young crater that had punched through that layer of surface debris, and point a spectrometer directly at a rock ejected from that crater. But this meant the far side of the moon, a place where direct communication with Earth was impossible, a place where no one had ever landed before. And to solve this riddle, someone would have to land on that dark side of the moon for the first time in history. But landing there wasn't just an engineering challenge. It was about answering one of the most fundamental questions about how the moon itself came to be. Because finding that missing mantle wasn't just about solving a geological puzzle. It was about finding evidence for the moon's moment of birth, one of the most violent events in the solar system. So, to understand why the mantle is so important, we need to go back much further than this impact, to a decades-long debate about the moon's formation. And at the center of this debate was a radical idea proposed in 1975 by two American planetary scientists, William Hartmann and Donald Davis. Their proposal was simple, but shocking. The moon had not formed slowly and gently alongside the Earth. The moon was born of violence. It was the product of a single, grazing collision between the young Earth and an object roughly the size of Mars. They argued that the debris from this impact formed a disk around the young Earth, and the moon slowly coalesced from this disk. This hypothetical impactor would later be given a name, Theia. This idea didn't get much traction at first, because the scientific community was busy with other theories, each with its own fatal flaw. So, there were three main competing theories on the table, and each solved one puzzle, but failed at another. The first was the capture theory. This theory suggested the moon formed elsewhere and was later captured by Earth's orbit. But capturing an object of this size, without destroying it or flinging it back into space, requires an extremely narrow and near impossible set of initial velocities and angles. It was the kind of coincidence that orbital mechanics rarely gives for free. The second was the fission theory. This theory proposed that the young, rapidly spinning Earth flung a piece of itself into space, like a fast-spinning ball of dough throwing off a small chunk. But no one could find a physically realistic spin rate that could do this without completely shattering the planet. The third was the co-formation theory. This theory suggested that the Earth and Moon formed side by side from the same part of the solar nebula. It was clean and simple. However, this theory didn't explain why the moon's core is so small relative to Earth's, despite both bodies condensing from the same initial material. It was in the midst of this theoretical turmoil that everything changed before a conference in Hawaii in 1984. 3 scientists issued a challenge to their colleagues. You have 18 months. Go back to the Apollo data, go back to the models, and decide what happened, because you no longer had the option to remain undecided. And at that conference, the giant impact hypothesis emerged as the clear frontrunner, because it explained everything the other theories could not. It explained why the moon has such a small iron core, because a grazing impact would tear off more of the rocky mantles of both bodies than their metallic cores. It explained why the Earth-Moon system has such a high angular momentum, and it explained why the lunar rocks brought back by the Apollo missions are so similar to Earth's mantle. But this very last point became the hypothesis's most stubborn problem, because if the moon was mostly formed from Theia, and Theia was a completely different body, the isotopic match between Earth and the moon should not have been so close. A striking idea put forth in 2018 to solve this puzzle suggested that the collision was energetic enough to transform both bodies briefly into a single, huge, bloated, donut-shaped structure called a synestia. Within this structure, material from Earth and Theia had time to mix thoroughly before recondensing to form first the Earth and then the moon. This is why the missing mantle problem wasn't just a curiosity about a basin. If the moon's mantle could be directly sampled, it would give the giant impact hypothesis something it had never had before, a second, independent data point on what the moon's deep interior was made of. All these theories, all these debates, remained an open question on the table until China's lunar exploration program reached the point where landing on the far side became possible. And at that exact moment, China entered the stage. They named their program after the goddess who, in Chinese mythology, was said to live alone on the moon, Chang'e, and each mission carried forward a small piece of this mythology. Chang'e 1 and 2 were orbiters launched in 2007 and 2010. Their purpose was to map the lunar surface in increasing detail and to rehearse the navigation required for an eventual landing, because that was the real goal. And in 2013, Chang'e 3 landed China's first lander and first rover, U2, on a plane on the near side of the moon. This was a historic moment, occurring in an era when no nation had soft landed on the moon for nearly 40 years. But the truly revolutionary step was yet to come, because Chang'e 4 was designed from the very beginning to be something far more ambitious. Therefore, instead of landing on the familiar near side again, the mission would attempt something no spacecraft had ever tried before: to land on that face that never looks at Earth, to a place where no signal could reach a spacecraft directly. And they would embark on a mission where success or failure would be known only through a relay satellite, built and launched specifically to make this attempt possible. This relay satellite alone was a huge step, because a relay satellite that sits usefully between the Earth and the moon's far side is a hard thing to fund on its own. No one wanted to bear such a cost for a destination that didn't yet have a specific scientific target. But China took that step, and the name of that step was Queqiao. It meant Magpie Bridge. The name was taken from a Chinese folktale about a bridge of magpies that forms once a year across the Milky Way to unite two lovers. The satellite was launched in May 2018, 7 months before the main mission. Its target was the second Lagrange point of the Earth-Moon system. This point is located about 65,000 kilometers beyond the far side of the moon. An object placed here remains in a fixed position relative to both bodies, thanks to their combined gravity. Queqiao was not placed at that exact point, but into a wide halo orbit, rotating around it. From this orbit, it could see both the Earth and the far side of the moon simultaneously. It was the only spacecraft in history to occupy this position. This detail is worth dwelling on, because the far side of the moon never sees the Earth. Not once, not briefly, not from any angle. If you were standing on the floor of that basin, there would be no blue marble waiting for you in the sky. But Queqiao, at that very point, was the only thing that saw both sides of this divide at the same time. And if it failed, the entire mission would have been lost in silence. Because the far side of the moon is completely insulated from radio waves from Earth. No signal can pass through 3,474 kilometers of solid rock. Every command, every data packet, every image from Chang'e 4 had to go first to Queqiao, and then from Queqiao to Earth. The team in the control center in Beijing had no direct line to their spacecraft. They were literally talking through a mirror placed in space for this very purpose. And if the mirror cracked, there would be nothing on Earth that could hear the lander. On December 7th, 2018, a Long March 3B rocket lifted off, carrying the Chang'e 4 lander and the Yutu-2 rover. Their target was to land on the floor of the 186-kilometer von Karman crater, inside that massive basin we mentioned earlier. There was a strange layer of history hidden in this name. The crater was named after the Hungarian-American engineer Theodor von Karman, but one of von Karman's most talented students was a young Chinese engineer, then known in the West as Shui Shen-tsian. Tsian was unjustly accused of communist sympathies in the 1950s. His security clearance was revoked, and he was finally deported to China in 1955. Tsian became the founder of China's own rocket and space program. 60 years later, the institutions he founded would land a spacecraft in a crater bearing the name of the mentor he was forced to leave. And now comes the real shock. On January 3rd, 2019, the lander began its descent. The final phase was very fast. Even with the relay, the communication delay was so great that no human could have manually flown it. So, the landing sequence was pre-programmed. Every burn, every adjustment, every moment the lander would check its altitude against the terrain below and correct its course was all written in advance. And there was nothing the engineers in the control room in Beijing could do. They just watched the slightly delayed data come in and waited. At 10:26 a.m. Beijing time, the lander touched the surface. A few hours later, the first image arrived, a grey, slightly undulating plain, dotted with small craters and rocks. And it stretched to a horizon no human had ever seen from the ground. Because this was a triumph. For the first time in human history, a soft landing had been made on the far side of the moon. A few hours later, the Yutu-2 rover rolled down the ramp. It was named after the jade rabbit, the companion of the moon goddess Chang'e in Chinese mythology. It weighed about 140 kilograms. It was the size of a small table. It had 6 wheels, a mast carrying a panoramic camera, and 2 main scientific instruments, a spectrometer and a ground-penetrating radar. Its maximum speed was less than half a meter per minute. You could not walk at that speed. It was made to look carefully. But there was a reason for this slowness, because its predecessor had not been so lucky. The Yutu-1, which landed on the near side in 2013, had suffered a control circuit failure in the middle of its second lunar day and never moved again. The engineers of Yutu-2 had learned from that mistake. So, the rover began to move slowly across the plain. It stopped to study rocks. It took panoramas. It sent radar signals into the ground and listened for the echoes. It had no schedule to keep. Its only job was to look patiently at whatever the floor of the basin put in front of it. And in May 2019, less than 5 months after landing, this patience produced something specific. The rover had been moving across the basaltic plain for weeks. A crater began to take shape in front of it. First a slight rise, then a low rim of ejected rocks, and finally a bowl about 72 meters wide. The crater was young. On the moon, youth is relative. It might have formed a few million, or perhaps a few tens of millions of years ago. What was important was that the material it had ejected was fresh enough that it hadn't yet mixed into the surrounding regolith. The rocks on its rim were angular, broken, their surfaces clean. They had come from the depths. And in this part of this basin, depth meant everything. The rover stopped near the rim of the crater, and it pointed its spectrometer at one of the ejected rocks. The reading went back to the control center in Beijing and to the scientists at the National Astronomical Observatories of the Chinese Academy of Sciences. When the spectral curve appeared on their screens, a particular silence fell over the room. This was not the silence of confusion. This was the silence of recognition, because the spectrum showed two deep absorption features. One was the signature of low calcium pyroxene. The second was the signature of olivine. Together, these two minerals pointed to a type of rock composed almost entirely of olivine and pyroxene. These were mantle rocks, and they had no business being on the surface of a crust. The missing mantle problem, that quiet puzzle of decades, had finally found an answer. The mantle wasn't missing, it was just hidden. The great impact had indeed excavated the deep interior of the moon and scattered it across the basin floor. But for 4 billion years, lava flows had covered it, and smaller impacts had concealed the surface. Only a fresh, small impact, namely this exact 72-meter crater, could have punched through the top layers to reveal what lay beneath. And Yutu, too, was in the right place at the right time. But how could this single reading be so definitive? What exactly did the spectrometer see, and why was it so important? Now, let's get technical. Because that small instrument on Yutu-2's mast was using a fundamental principle of physics known for decades to solve a mystery, and that principle is called orbital spectroscopy. This is the technique of identifying minerals from reflected sunlight. Just as every person has a unique fingerprint, every mineral has a unique light signature. Because different minerals absorb specific wavelengths of sunlight, and they create characteristic patterns that a spectrometer can read from orbit. So, the instrument doesn't take a picture in the conventional sense. It takes a reading. It plots a curve of brightness versus wavelength. And the dips and peaks of this curve encode the mineralogy of what it's looking at. Therefore, the rover's spectrometer was designed to measure the intensity of reflected sunlight across a range of wavelengths, from the visible blue to the near infrared. When sunlight hits a mineral, certain wavelengths are absorbed by the chemical bonds within its crystal structure. Olivine absorbs light in a broad area around 1 micrometer. Pyroxene absorbs in 2 narrow bands near 0.9 and 1.9 micrometers. Plagioclase feldspar, the dominant mineral of the lunar crust, absorbs at a completely different wavelength and much more weakly. These signatures are so distinct that there is almost no difference between a rock a geologist looks at in a lab and a rock a rover looks at from millions of kilometers away. The fundamental chemistry is the same. Because this technique had been refined since the Apollo era, Clementine carried a spectrometer. So did India's first lunar mission, Chandrayaan-1, launched in 2008. So did the Lunar Reconnaissance Orbiter and Japan's Kaguya Orbiter. They all mapped the surface composition of the basin, and they all found the same thing. On the basin floor, anorthosite was dominant. In other words, crustal material. That's why Yutu-2's reading was so shattering, because the spectrum from the crater rim wasn't a subtle variation on a crustal theme. This was a completely different song. Those two deep absorption features in the spectrum, pyroxene and olivine, were too clear to be misinterpreted. This was something that no instrument looking from orbit for decades had been able to see, because they were all looking at the surface layer of dust and debris. But that 72-meter fresh crater had pierced this veil and revealed the truth beneath. But the spectrometer answered only one question. The larger question of what was beneath the rover was still unanswered. So, Yutu-2 was equipped with a second powerful tool, ground-penetrating radar. This technology is not exotic in itself. Archaeologists use a version of the same instrument to map buried walls and foundations without digging a single trench. Construction engineers use it to check for voids and pipes under a road before deciding where to drill. The principle is the same in every case. You send a radio pulse down, you listen for the echo that bounces back. And using the timing and strength of the echo, you deduce what's under the ground that you can't otherwise see. It was like an ultrasound of the moon's shallow subsurface. And it was asking a different question than the spectrometer. The spectrometer had asked what a single rock was made of. The radar was asking what happened here, in sequence, over the last 4 billion years. Because the radar instrument on U-22 was a 2-channel system. The high-frequency channel operated at 500 MHz. It sent short pulses into the ground and listened for reflections from boundaries spaced a few centimeters apart. It saw fine detail, but only down to about 12 meters deep. The low-frequency channel operated at 60 MHz. It penetrated deeper to about 40 meters, but with lower resolution. Together, they created a vertical profile of the ground beneath the rover's wheels. And this profile revealed a history of billions of years of violence, layer by layer. The first 12 meters were relatively uniform. The reflections were weak and featureless. This was the modern regolith. The crushed, gardened surface layer, produced by billions of years of micrometeorite bombardment. On the moon, there is no wind or rain to turn the soil. But there is a constant, gentle rain of particles the size of dust and sand grains traveling at tens of kilometers per second. Each one strikes the surface rock, shattering it and producing a fine dust. But below 12 meters, the low-frequency channel revealed something more structured. A series of alternating coarse and fine layers extending down to 40 meters deep. The coarse layers produced strong, irregular reflections. This indicated a pile of rocks and boulders. These were interpreted as ejector blankets, thrown out by an impact from a nearby location. The fine layers between them were paleo-regoliths, that is, ancient surfaces. These had been exposed long enough to develop their own thin coating of dust from micrometeorites, before the next nearby impact buried them again under a fresh blanket of debris. So, the radar was not seeing a single event. It was seeing many events, stacked on top of each other in time, like the pages of a book no one had opened for billions of years. The floor of the basin was not a single homogeneous lava plain. It was a surface written and rewritten by a long series of smaller, more recent craters. But behind these layers lay an even deeper mystery, because in 2022, a more detailed reanalysis of the same radar data identified a particularly strong, continuous reflective boundary about 17 meters below the surface. This was interpreted as a buried crater floor, completely sealed off by later debris. And the radar properties of the material below this boundary were different. More homogeneous, less reflective. Perhaps a mixture of impact melt and deeply rooted rocks that had never been reworked by later gardening. Some scientists suggested that this material could be associated with the mantle-derived rocks the spectrometer found on the surface. In other words, that 17-meter boundary could be the very layer of buried debris that the small nearby crater had finally pierced. But this interpretation was controversial because radar measures density contrasts, not chemistry. A reflection tells you that two materials are different from each other, but it doesn't tell you what either of them is made of. Therefore, there had to be a mechanism that could preserve such a deep history, and the name of that mechanism is the absolute stillness of the moon. On Earth, wind, rain, and plate tectonics erase the record of most impacts within a few million years. Very few rocks old enough to remember the era when this basin formed are left on our planet. But on the moon, there is no equivalent erosion. The only processes that change the surface are impacts and, in the distant past, volcanism. And volcanism mostly stopped more than 1 billion years ago. A crater formed 4 billion years ago still looks like a crater. A debris blanket buried 3 billion years ago is still structurally a debris blanket. The moon is a geological fossil, and because the far side was never resurfaced, like the Maria of the near side, it is the most pristine half of that fossil. Those layers beneath the von Karman crater are not just a record of the moon, they are an extension of our own planet's history, preserved in the only surviving archive. But there was a second type of preservation at work here, and it had nothing to do with rocks. It was hidden not in the layers beneath your feet, but in the air that wasn't there. The far side of the moon is the only place in the inner solar system naturally shielded from all terrestrial radio noise. The moon's 3,474-kilometer mass of rock blocks any and all broadcasts from Earth. This silence is not just deep, it is orders of magnitude deeper than the quietest place on Earth. Even the best radio quiet zones on our planet have to contend with the ionosphere, with distant transmitters, with the faint hum of power lines and satellites passing overhead. But on the far side of the moon, there is none of that. There is only rock, vacuum, and cold. And this silence is hiding something that has been traveling for over 13 billion years. Because, according to the standard model of cosmology, the universe began in a hot, dense state and expanded. For the first 380,000 years, it was so hot that matter existed as a plasma. The universe was opaque, light could not travel freely. But then, when the temperature dropped below about 3000 Kelvin, electrons and protons combined to form neutral hydrogen atoms, and the fog lifted. The photons that had been trapped within the plasma were suddenly set free. We detect them today as the cosmic microwave background. But for a long time after that moment, there were no stars. The first stars began to shine about 150 million years later. That period in between is called the Dark Ages, and there are no directly detected electromagnetic signals from that era. But every hydrogen atom in that gas was occasionally flipping the spin of its single electron, and in the process, emitting a photon with a wavelength of 21 centimeters. This is the most famous spectral line in radio astronomy. And during the Dark Ages, it was being sung by the entire universe at once, in a single note. That very note has been stretched by the expansion of the universe itself. What was emitted at 21 centimeters has been redshifted to much longer wavelengths, up to several meters. This is a part of the radio spectrum that is almost impossible to observe from the ground, because the ionosphere blocks most of it, and what little gets through is drowned out by the noise of our own civilization's radio broadcasts. A signal from the Dark Ages is a whisper by the time it reaches Earth. But on Earth, that whisper is drowned out by a stadium crowd. On the far side of the moon, there is no stadium crowd. That silence holds a map of what the universe was like before the first star ever shone. That faint, structured signal. This is the only direct observational window we know of into an era that is otherwise, by definition, dark. And the key to opening that window was hidden on the very relay satellite for Chang'e 4, Keqiao, because Keqiao carried a technology demonstration jointly developed by Dutch and Chinese teams. 3 monopole antennas, each 5 meters long. Their purpose was to listen to the low-frequency radio sky from the satellite's unique vantage point, and they succeeded. The instrument recorded the low-frequency radio emission of the Milky Way itself. It did not detect the Dark Ages signal. That would require something much larger. But it proved that the basic idea worked. A receiver sitting in the radio shadow of the far side could indeed hear things that no instrument on Earth could ever hear. And now comes the real shock. Because those preserved layers under the von Karman crater were not just storing the history of the moon, but also our own history. An impact carrying 500 million times the energy of humanity's greatest weapon could not have just happened to a planet with a nearby neighbor. It happened to Earth, too, because the moon orbits the Earth just 380,000 kilometers away. Statistically, whatever hit one body was almost certainly part of the same population of debris that was crossing the path of the other. And Earth was a much bigger target than the moon. with a much stronger gravity to pull in anything that passed nearby. Its gravitational cross-section was about 20 times that of the Moon. This meant one simple thing. For every object that hit the lunar surface in that era, about 20 similar objects hit the Earth. Therefore, an impact of the size that carved out that basin could not have just happened to the Moon and somehow missed its neighbor. The probability of that over the hundreds of millions of years of this period was effectively zero. So, what would an impact like that do to a planet with oceans and an atmosphere, instead of a bare rocky surface? The answer was horrifying. The basin-forming event alone melted and vaporized thousands of cubic kilometers of rock on the Moon. On Earth, the result would have been even worse. A transient crater, at least 1,000 kilometers wide, a wound that pierced the crust and mantle, molten rock ejected into orbit, some of it falling back as a burning rain, some of it escaping entirely. An atmosphere superheated in a way that resembled nothing breathable. Oceans turned to steam. For months, perhaps years, the surface would have been a roaring inferno under a sky glowing with the heat of recondensing rock vapor. The ground-level pressure alone would have been enough to sterilize anything still clinging to a foothold. And it didn't just happen once. The cratering record on the Moon includes not just this basin, but hundreds of smaller, large basins and thousands of smaller craters. This means that during Earth's Hadean eon, it was hit by thousands of objects larger than 10 kilometers and dozens larger than 100 kilometers. Whether there was a single discrete spike in this bombardment rate around 3.9 billion years ago is still hotly debated among experts. But even setting aside the question of a spike, the background impact rate in this age was orders of magnitude higher than today's. For its first few 100 million years of existence, Earth lived inside a shooting gallery with no walls. But the truly impossible thing was this. The evidence of all this on Earth has been almost completely erased. The oldest known rocks on our own planet, the Augusta gneiss from Canada's Northwest Territories, are about 4.03 billion years old. Even they have been heated, squeezed, and chemically altered by later geological processes. And they are from a time when the worst of the bombardment was already over. Before that, there is nothing. Not a single rock is left on Earth from the first 500 million years of the planet's existence. It is a complete blank in the geological record. The only witnesses left from that lost era are zircons. These are tiny crystals of zirconium silicate that form inside granitic magmas and are exceptionally resistant to later alteration. The oldest known zircons, recovered from the Jack Hills of Western Australia, date back as far as 4.4 billion years. They are smaller than a grain of sand, but they carry chemical and isotopic clues about the conditions under which they crystallized. Because the oxygen isotope ratios in these zircons suggest that, despite everything we know about the impact rate at the time, liquid water was already present on Earth's surface at that point. This was an incredibly early and surprisingly cool history. The zircons seem to contradict the picture of a permanent hellscape surface at first glance. But zircons are the survivors, and survivors are not always representative. They may be recording brief, local windows of relatively stable conditions that opened up between successive sterilizing impacts. The bombardment was intense, but it wasn't continuous. Between the largest impacts, the surface may have cooled enough for water to condense and for the first fragments of a stable crust to begin to form, before the next big one reset the clock entirely. This is why the lunar record is so crucial for people who study the early Earth. If you know the impact rate on the Moon, you can calculate the impact rate the Earth experienced during the same period. If you know when the Moon's big basins formed, you know roughly when Earth was most likely sterilized as well. But within this violence lay a strange complexity, a puzzle that planetary scientists have long tried to solve. The same bombardment that had the capacity to completely sterilize a planet also appears to be the main way a young, rocky world acquired most of its water and carbon-based chemistry. Models of early planet formation generally suggest the inner solar system formed too hot and too dry for much water to condense directly from the material that made up Earth's crust and mantle. In most current models, a significant fraction of what eventually became our oceans likely arrived later, delivered by comets and water-rich asteroids during this same chaotic era of impacts. The same kind of impact that could boil an ocean in one instance could be silently delivering the raw materials for the next ocean in countless smaller instances spread over the same few 100 million years. Violence and habitability, based on the current evidence, were not opposite concepts in this period. They were, uncomfortably, the same process, just observed at different scales and at different moments. This basin doesn't answer that question. It just records, with unusual clarity, what an answer looked like the last time the impact scale was at its worst. But this story isn't just about past violence, because the same basin that records the worst of that violence is also bordered by something that has nothing to do with destruction. On the southern rim of the Great Basin, where its edge rises toward the pole, there are craters whose floors have not seen sunlight, not once. The moon's axis of rotation is tilted by only about 1.5 degrees relative to its orbital plane. On Earth, a tilt of about 23.5 degrees gives us our seasons. But on the moon, there are no seasons. The sun circles low on the horizon at the poles, never rising more than a few degrees, and any depression deep enough to sit permanently in the shadow of its own rim remains in darkness, literally forever. These are called permanently shadowed regions. In that permanent darkness, temperatures can drop to about 30 Kelvin, colder than the surface of Pluto, just a few tens of degrees above absolute zero. Therefore, at these temperatures, water ice is stable over billions of years. It doesn't sublimate, it doesn't migrate, it just stays where it lands, molecule by molecule, slowly accumulating from comet impacts and solar wind interactions. These craters are cold traps, and they have been collecting water for most of this history. The first hints came in 1994 from the Clementine orbiter. It bounced a radio signal off the permanently shadowed floor of Shackleton crater near the South Pole. The reflection it got back on Earth showed properties consistent with water ice, but the result was more suggestive than conclusive. In 1998, Lunar Prospector carried a neutron spectrometer that measured the energy of neutrons reaching it from the lunar surface. And over the lunar poles, it found a significant suppression in mid-energy neutrons. This pointed to an abundance of hydrogen, and thus likely water. But it was not yet a smoking gun, because the definitive answer came in October 2009 from a mission whose design was simple enough to be described in a single sentence. Throw something heavy at a permanently shadowed crater, hard, and watch what comes up. The Lunar Crater Observation and Sensing Satellite steered a spent Centaur rocket stage, weighing about 2,300 kilograms, into Cabeus Crater near the South Pole. The Centaur hit at about 2.5 kilometers per second. It excavated a crater 20 to 30 meters wide and threw a plume of material more than 10 kilometers above the surface. The actual result required weeks of careful spectral analysis. It turned out that about 5.6% of the ejected material by mass was water ice. Alongside it were other volatiles like carbon monoxide, carbon dioxide, ammonia, and methane. The permanently shadowed craters at the lunar poles were not dry. They were cold, dark reservoirs of the very raw materials that life requires, and that any sustainable human presence beyond Earth will eventually need. It took a few years for the implications of this discovery to fully settle in, but once they did, they reshaped everything. Water is heavy, and every kilogram launched from Earth costs tens of thousands of dollars in fuel and engineering. Water available on the lunar surface changes that equation completely. When separated into hydrogen and oxygen by electrolysis, it becomes both breathable air and rocket fuel. Water on the moon turns the moon from a destination into a filling station, the South Pole, not the historically familiar near side, is now the focus of almost every planned mission. NASA's Artemis program plans to land astronauts there within the decade. China's next step, Chang'e 7, is targeting the illuminated rim right next to Shackleton crater. Russia, India, Japan, and the European Space Agency all have their own South Pole missions in the works. The lunar South Pole in the 2020s has become what the near side was in the 1960s, the place nations go to show what they can do. But for all these calculations, the most valuable thing the far side has produced so far was not water, nor radio silence, nor any strategic advantage. It was a few kilograms of rock and soil. In 2024, China brought them home. Chang'e 6 launched on May 3rd, 2024. It was built on the architecture of Chang'e 5, which had successfully returned samples from the near side 4 years earlier. The mission's target was the Apollo Basin. Mission planners decided on this region after years of orbital reconnaissance because its floor combined two things that are rarely found together: a relatively young, smooth basaltic plain safe enough to try to land on, and it sat on top of older debris thought to contain material excavated directly from the moon's deep crust and upper mantle. This mission profile had no room for error. Every single step had to work the first time. On June 1st, 2024, the lander touched down on the floor of the Apollo Basin. Its sampling system combined a robotic scoop for surface material with a drill capable of reaching 2 meters below the surface. The total mass collected was just under 2 kilograms. 3 days later, the ascent vehicle lifted off from the top of the lander, the first launch in history from the far side of the moon. It climbed to orbit and performed an autonomous rendezvous with the orbiter. It transferred the sample container. 3 weeks later, the return capsule separated, entered Earth's atmosphere at over 11 kilometers per second, and parachuted down to the grasslands of Inner Mongolia. When the capsule was opened, the inside was clean. The seal had held. Inside were the first rocks and soil physically returned from the far side of the moon. And now we ask ourselves, in a laboratory in Beijing, inside a nitrogen-filled container, sits about 2 kilograms of rock and soil from the far side of the moon. This is the tangible result of a decades-long quest, an incredible engineering triumph and quiet patience. But now is the time to stop and think. Because this mission signifies so much more than just solving a geological puzzle or demonstrating a technological capability. It's about confronting our own existence in the midst of a 4.3 billion year silence. It's time to ask where we stand on this vast cosmic stage, what we mean within this deep time, and what that absolute silence is telling us. And now we face the most important question. Who are we? And where are we in this story? Because this discovery reveals one of the most fundamental contrasts between us and the universe, the contrast of time. On one hand, there is a basin formed between 4.2 and 4.3 billion years ago, a feature almost as old as the planet itself. That piece of rock has sat there silently for an unimaginable duration since it formed deep in the moon's mantle, first buried, then re-exposed, and, for millions of years, subjected to the slow erosion of solar wind and micrometeorites. On the other hand, there is the single moment that solved that 4.3 billion-year-old secret, May 2019. The entirety of human history is less than a blink of an eye compared to the time that rock has been waiting. Even the Yutu-2 rover that solved the secret was designed for a lifespan of only 3 months, a mere nothing on this colossal timescale. How is this possible? What does it mean that a 4 billion-year silence can be broken by a mission of just a few years and an analysis of just a few hours? It's a stark confrontation with the tragic brevity of our existence. An average human lifespan, about 80 years, is nothing more than statistical noise next to the age of that basin. The entire recorded history of our planet fits within just the last 1,000,000,000% of that geological time. Against the overwhelming scale of that silence, our existence is not even a moment. But right at this point, within that tragedy, lies an incredible beauty. Yes, we are just momentary flickers in this ocean of time. But in that brief moment, we possess the ability to read that 4.3 billion year past. We can look at the spectrum of that rock and understand where it was billions of years ago, how it formed, and how it reached the surface. Our consciousness is the only thing that can break the one-way flow of time, to look back and interpret the past. A rock does not know its own history. A basin does not care about its own age. But we, with our fleeting lives, can enter that silence and tell its story. This is our power. Our physical frailty against time is balanced by our mental strength. You are a part of this equation. Your own life may be nothing next to those 4.3 billion years. But right now, as you read these words, your mind is traversing that immense span of time. You are also listening to that silence, understanding that story. And that makes you so much more than a momentary flicker. This brings us to a second contrast, the contrast of scale. On one hand, there is a basin 2,500 kilometers wide, the size of a continent. Its depth is 13 kilometers. This is a scale our minds can barely grasp. If you stood in the middle, you wouldn't even realize you were in a crater. It would seem like a part of the Earth itself. On the other hand, there is the machine that reads this massive wound, U22, weighing only 140 kilograms, the size of a small table, and the evidence that machine found is a curve of a few pixels on a screen, a spectrometer reading. And the ultimate proof brought by Chang'e 6 is a handful of soil, small enough to fit in your palm, just 2 kilograms. This is a comparison that shows our place in the cosmic scale in the most brutal way. We are physically nothing next to these massive structures. In that geography, even an astronaut would just be a moving speck of dust. Our strength, our speed, our endurance are comically inadequate against the indifferent vastness of that landscape. Rate on the Moon, you can calculate the impact rate the Earth experienced during the same period. If you know when the Moon's big basins formed, you know roughly when Earth was most likely sterilized as well. But within this violence lay a strange complexity, a puzzle that planetary scientists have long tried to solve. The same bombardment that had the capacity to completely sterilize a planet also appears to be the main way a young, rocky world acquired most of its water and carbon-based chemistry. Models of early planet formation generally suggest the inner solar system formed too hot and too dry for much water to condense directly from the material that made up Earth's crust and mantle. In most current models, a significant fraction of what eventually became our oceans likely arrived later, delivered by comets and water-rich asteroids during this same chaotic era of impacts. The same kind of impact that could boil an ocean in one instance could be silently delivering the raw materials for the next ocean in countless smaller instances spread over the same few 100 million years. Violence and habitability, based on the current evidence, were not opposite concepts in this period. They were, uncomfortably, the same process, just observed at different scales and at different moments. This basin doesn't answer that question. It just records, with unusual clarity, what an answer looked like the last time the impact scale was at its worst. But this story isn't just about past violence, because the same basin that records the worst of that violence is also bordered by something that has nothing to do with destruction. On the southern rim of the Great Basin, where its edge rises toward the pole, there are craters whose floors have not seen sunlight, not once. The Moon's axis of rotation is tilted by only about 1.5 degrees relative to its orbital plane. On Earth, a tilt of about 23.5 degrees gives us our seasons. But on the Moon, there are no seasons. The Sun circles low on the horizon at the poles, never rising more than a few degrees, and any depression deep enough to sit permanently in the shadow of its own rim remains in darkness, literally forever. These are called permanently shadowed regions. In that permanent darkness, temperatures can drop to about 30 Kelvin, colder than the surface of Pluto, just a few tens of degrees above absolute zero. Therefore, at these temperatures, water ice is stable over billions of years. It doesn't sublimate, it doesn't migrate, it just stays where it lands, molecule by molecule, slowly accumulating from comet impacts and solar wind interactions. These craters are cold traps, and they have been collecting water for most of this history. The first hints came in 1994 from the Clementine orbiter. It bounced a radio signal off the permanently shadowed floor of Shackleton crater near the South Pole. The reflection it got back on Earth showed properties consistent with water ice, but the result was more suggestive than conclusive. In 1998, Lunar Prospector carried a neutron spectrometer that measured the energy of neutrons reaching it from the lunar surface. And over the lunar poles, it found a significant suppression in mid-energy neutrons. This pointed to an abundance of hydrogen, and thus likely water. But it was not yet a smoking gun, because the definitive answer came in October 2009 from a mission whose design was simple enough to be described in a single sentence. Throw something heavy at a permanently shadowed crater, hard, and watch what comes up. The Lunar Crater Observation and Sensing Satellite steered a spent Centaur rocket stage, weighing about 2,300 kilograms, into Cabeus Crater near the South Pole. The Centaur hit at about 2.5 kilometers per second. It excavated a crater 20 to 30 meters wide and threw a plume of material more than 10 kilometers above the surface. The actual result required weeks of careful spectral analysis. It turned out that about 5.6% of the ejected material by mass was water ice. Alongside it were other volatiles like carbon monoxide, carbon dioxide, ammonia, and methane. The permanently shadowed craters at the lunar poles were not dry. They were cold, dark reservoirs of the very raw materials that life requires, and that any sustainable human presence beyond Earth will eventually need. It took a few years for the implications of this discovery to fully settle in. But once they did, they reshaped everything. Water is heavy, and every kilogram launched from Earth costs tens of thousands of dollars in fuel and engineering. Water available on the lunar surface changes that equation completely. When separated into hydrogen and oxygen by electrolysis, it becomes both breathable air and rocket fuel. Water on the moon turns the moon from a destination into a filling station. The South Pole, not the historically familiar near side, is now the focus of almost every planned mission. NASA's Artemis program plans to land astronauts there within the decade. China's next step, Chang'e 7, is targeting the illuminated rim right next to Shackleton crater. Russia, India, Japan, and the European Space Agency all have their own South Pole missions in the works. The lunar South Pole in the 2020s has become what the near side was in the 1960s, the place nations go to show what they can do. But for all these calculations, the most valuable thing the far side has produced so far was not water, nor radio silence, nor any strategic advantage. It was a few kilograms of rock and soil. In 2024, China brought them home. Chang'e 6 launched on May 3rd, 2024. It was built on the architecture of Chang'e 5, which had successfully returned samples from the near side 4 years earlier. The mission's target was the Apollo Basin. Mission planners decided on this region after years of orbital reconnaissance because its floor combined two things that are rarely found together: a relatively young, smooth basaltic plain safe enough to try to land on, and it sat on top of older debris thought to contain material excavated directly from the moon's deep crust and upper mantle. This mission profile had no room for error. Every single step had to work the first time. On June 1st, 2024, the lander touched down on the floor of the Apollo Basin. Its sampling system combined a robotic scoop for surface material with a drill capable of reaching 2 meters below the surface. The total mass collected was just under 2 kilograms. 3 days later, the ascent vehicle lifted off from the top of the lander. The first launch in history from the far side of the moon. It climbed to orbit and performed an autonomous rendezvous with the orbiter. It transferred the sample container. 3 weeks later, the return capsule separated, entered Earth's atmosphere at over 11 kilometers per second, and parachuted down to the grasslands of Inner Mongolia. When the capsule was opened, the inside was clean. The seal had held. Inside were the first rocks and soil physically returned from the far side of the moon. And now we ask ourselves, in a laboratory in Beijing, inside a nitrogen-filled container, sits about 2 kilograms of rock and soil from the far side of the moon. This is the tangible result of a decades-long quest, an incredible engineering triumph and quiet patience. But now is the time to stop and think. Because this mission signifies so much more than just solving a geological puzzle or demonstrating a technological capability. It's about confronting our own existence in the midst of a 4.3 billion year silence. It's time to ask where we stand on this vast cosmic stage, what we mean within this deep time, and what that absolute silence is telling us. And now we face the most important question. Who are we? And where are we in this story? Because this discovery reveals one of the most fundamental contrasts between us and the universe, the contrast of time. On one hand, there is a basin formed between 4.2 and 4.3 billion years ago, a feature almost as old as the planet itself. That piece of rock has sat there silently for an unimaginable duration since it formed deep in the moon's mantle, first buried, then re-exposed, and, for millions of years, subjected to the slow erosion of solar wind and micrometeorites. On the other hand, there is the single moment that solved that 4.3 billion-year-old secret, May 2019. The entirety of human history is less than a blink of an eye compared to the time that rock has been waiting. Even the Yutu-2 rover that solved the secret was designed for a lifespan of only 3 months, a mere nothing on this colossal timescale. How is this possible? What does it mean that a 4 billion-year silence can be broken by a mission of just a few years and an analysis of just a few hours? It's a stark confrontation with the tragic brevity of our existence. An average human lifespan, about 80 years, is nothing more than statistical noise next to the age of that basin. The entire recorded history of our planet fits within just the last 1,000% of that geological time. Against the overwhelming scale of that silence, our existence is not even a moment. But right at this point, within that tragedy, lies an incredible beauty. Yes, we are just momentary flickers in this ocean of time. But in that brief moment, we possess the ability to read that 4.3 billion year past. We can look at the spectrum of that rock and understand where it was billions of years ago, how it formed, and how it reached the surface. Our consciousness is the only thing that can break the one-way flow of time, to look back and interpret the past. A rock does not know its own history. A basin does not care about its own age. But we, with our fleeting lives, can enter that silence and tell its story. This is our power. Our physical frailty against time is balanced by our mental strength. You are a part of this equation. Your own life may be nothing next to those 4.3 billion years. But right now, as you read these words, your mind is traversing that immense span of time. You are also listening to that silence, understanding that story. And that makes you so much more than a momentary flicker. This brings us to a second contrast, the contrast of scale. On one hand, there is a basin 2,500 kilometers wide, the size of a continent. Its depth is 13 kilometers. This is a scale our minds can barely grasp. If you stood in the middle, you wouldn't even realize you were in a crater. It would seem like a part of the Earth itself. On the other hand, there is the machine that reads this massive wound, Yutu-2. weighing only 140 kilograms, the size of a small table, and the evidence that machine found is a curve of a few pixels on a screen, a spectrometer reading. And the ultimate proof brought by Chang'e 6 is a handful of soil, small enough to fit in your palm, just 2 kilograms. This is a comparison that shows our place in the cosmic scale in the most brutal way. We are physically nothing next to these massive structures. In that geography, even an astronaut would just be a moving speck of dust. Our strength, our speed, our endurance are comically inadequate against the indifferent vastness of that landscape. But again, we make a turn with the word but, because our physical smallness is overshadowed by the reach of our minds. Our bodies may be a dot within that basin, but our mind can encompass the entire basin. That 2,500 kilometer distance, that 13 kilometer depth, that 4.3 billion year history, we can understand it from where we sit, using only data and models. Our mind is a scale that transcends the limits of our physical presence. That table-sized rover is an extension of our mind. That 2 kilogram sample is a piece of evidence our mind can touch. We explore the universe not with our muscle power, but with our capacity to understand. And this turns our smallness not into a weakness, but into a starting point. You possess this power too. Your body may be within the confines of this room, but your mind is currently wandering the floor of that giant basin on the far side of the moon, imagining that silence, feeling that cold. You too are traveling beyond your physical limits with meaning and knowledge. This is one of the most fundamental miracles of being human. And this leads us to the deepest contrast, the contrast of silence and meaning. The far side of the moon is the most radio-silent place in the inner solar system. There, for billions of years, literally nothing happened, except for impacts. But no wind, no water, no life, just absolute silence, rock, vacuum, and cold. That basin wasn't hiding a secret, because for a secret to exist, there must be a consciousness to wonder about it. That rock wasn't waiting to be found, because expectation requires a mind. For 4.3 billion years, the universe was utterly indifferent. Only the laws of physics were at work there. There was no purpose, no intent, no meaning. This is the purest form of cosmic loneliness. Without us, the universe is just a machine that exists, but is not aware of itself. But we exist. We are noisy, complex, curious beings, and when we look at that silence, we don't just see a void, we see a story there. When we look at that spectral curve, we don't just see a graph. We see the moon's mantle, the birth of a planet, the violence of an impact. We are the beings who imbue the universe with meaning. It is we who take that silence and turn it into knowledge, wisdom, and even art. Even if we don't give that 72-meter crater a name, it is we who define it as a site of discovery. It is we who call that rock mantle material. It is we who try to listen for the dark ages signal within that silence. Without us, that signal is just a meaningless radio wave. With us, it becomes a window into the beginning of the universe. You are at the center of this meaning-making process. Your consciousness is taking these words and turning them into a story in your own mind. You are one of those rare beings who looks at that indifferent universe and finds an order, a beauty, and a meaning in it. And this, perhaps, is the most profound result of all these discoveries. And this search for meaning forces us to confront another deep paradox, that of destruction and creation. On one hand, there is an act of unimaginable destruction, so violent it could nearly split a world in two. That impact was an event that melted thousands of cubic kilometers of rock, that could boil an ocean, that could strip an atmosphere. This is the purest, most indifferent violence of the universe. On the other hand, there is the incredible opportunity for creation that this destruction offers us. Without that impact, the moon's mantle would never have been exposed. Without that mantle material, we would not have had the chance to test one of our most fundamental theories about how the moon, and therefore the Earth, formed. Destruction became the source of our deepest knowledge. How is this possible? What does it mean that the most violent events give birth to the most gentle moments of understanding? This is one of nature's most fundamental lessons. The universe is not good or evil, it just is. And the most destructive forces are also the most creative. Therefore, the tragic side of this paradox is that we need pain and loss to move forward. That basin is the scar of a trauma that happened billions of years ago, and we learn by reading that scar. It is the same in our own history. Our greatest breakthroughs often come after our greatest crises. Our deepest wisdom is often born from our deepest pain. Destruction is the engine of change, and change is sometimes painful. The universe reminds us that nothing comes for free, that even knowledge has a price. That price, in this case, is the near destruction of a world billions of years ago. But within this tragedy, there is also an incredibly hopeful truth, because it shows that no end is truly an end. That impact might have seemed like an end for that region of the moon, but it was also a beginning for us, billions of years later. The beginning of understanding. Destruction creates new forms, chaos gives birth to new orders, and even the darkest moments can carry the seeds of a future enlightenment. This is the most universal story of resilience and rebirth. You are a part of this cycle. You have experienced destructions and creations in your own life. The things you lost made you stronger, wiser. Your hardest moments became your greatest opportunities for growth. You too, like that lunar basin, carry the scars of your past. But those scars are proof not just of pain, but also of who you are and what you have learned. And this brings us to perhaps the most human contrast, the contrast of loneliness and connection. U-22 is alone on the far side of the moon. It cannot receive a direct signal from Earth. Like the jade rabbit in Chinese mythology, it is all alone in that silent, desolate world. This is one of the most poignant images of humanity's exploration of space. A machine working in absolute silence, hundreds of thousands of kilometers from the nearest intelligent life form. This is a metaphor for our cosmic loneliness. In this vast universe, as far as we know, we are also alone. We are listening for that dark ages signal, but we have not yet heard an answer. This is both an exciting and a slightly frightening thought. Could we be the only beings in this infinite void who search for meaning, who ask questions? This is the heaviest burden of that silence. But this loneliness is only half of the story, because U-22 is actually never alone. It is an extension of a team of hundreds of engineers and scientists on Earth. It is in constant communication with us through the Queqiao relay satellite. It is our eyes, our ears, and our hands. And that rover is not just a success for China. It is a success for humanity. It is the result of the accumulated knowledge of countless generations who have looked up at the sky and wondered, who invented rockets? Who calculated orbital mechanics? It is the legacy of Newton, of Kepler, of Tsiolkovsky, of von Karman, and of Tien. And it creates a connection with everyone who listens to this story. This mission is something that transcends national borders, that unites us in a common desire for curiosity and exploration. You are a part of this connection. Right now, through these words, you are connecting with that lonely rover. You are seeing what it sees, learning what it found, and you are connecting with the millions of other people who share this story. We may be physically separate, but in the network of knowledge and curiosity, we are all connected. And this, perhaps, is the most powerful antidote to that cosmic loneliness. S.O. Yes, we are brief against time, tiny against scale, noisy against silence, and alone against the universe. But We are also beings who can transcend time, comprehend scale, give meaning to silence, and connect with each other. These discoveries reveal a truth, not just about the moon, but about ourselves. They show us our fragility and our strength, our limits and our potential, all at the same time. They remind us how rare and how precious our place in this universe is. But this philosophical journey does not end here, because there is one more question that these discoveries have raised. This is a question not just about who we are, but also about where we are going. We now know that the far side of the moon is not just a geological archive, but also a resource for our future. So what will we do with this knowledge? And this question, what will we do, confronts us, not just with strategic decisions, but with a much deeper responsibility. Because what we found on the far side of the moon did not just open a window to the past. It also held up a mirror to the future. In that silence, in that pristine archive, there are not just geological facts, but also reflections of our own nature. So, now is the time to ask the most internal question. Armed with this knowledge, how will we play our role on this universal stage? This discovery has confronted us with the most fundamental paradoxes of being human, more sharply than ever before. The first of these paradoxes is the contrast between knowledge and unknowing. We went to the far side of the moon to find answers. We searched for the missing mantle. We tried to estimate the age of the basin. We mapped the layers of the subsurface, and we found some answers. 2, we learned that olivine and pyroxene are there, that there is a billion-year-old layer of debris beneath the surface, and that the impact had a violence beyond our imagination. But, on the other hand, every answer we found gave birth to new questions, much deeper and much more complex. We still do not know the precise age of that basin. We still do not know the overall composition of the lunar mantle. We still do not know the source of those mysterious magnetic anomalies. Even the question of whether the late heavy bombardment was a sudden spike or a slow decline has now become more important than ever. As the horizon of knowledge expands, so too does the ocean of unknowing beyond that horizon. How is this possible? How can our quest for knowledge bring us to the shore of even more mystery? The tragic side of this situation is that we may never reach the ultimate answers. The secrets of the universe may be infinite, but our time and resources are finite. Every puzzle we solve reveals itself to be just a piece of a larger puzzle. This is the melancholy that comes with accepting the limits of the human mind. No matter how far we go, no matter how deep we look, there will always be more. And this, in a way, means we are doomed to a journey that will never be complete. But at the very heart of this tragedy shines the most beautiful truth of being human. What defines us is not having answers, but asking questions. The force that drives us forward is not knowledge itself, but the desire to know. That ocean of unknowing is not an end, but an invitation. Every new question is an opportunity for a new discovery, a new adventure. If we knew everything, what would be left to wonder about? What would be left to explore? That unending quest is our greatest strength and our deepest source of meaning. You know this truth from your own life. Every new thing you learn reminds you of how little you know, but that doesn't stop you. On the contrary, it encourages you to learn more, because you are a being that grows not with answers, but with questions. This brings us to another, more concrete contrast, the contrast of presence and legacy. On one hand, there is the incredible fragility and transience of our presence on the lunar surface. The machines we send there are designed for a 3-month lifespan. A cottonseed dies in the freezing cold of a 2-week lunar night. The astronauts who will go there in the future will live in an unforgiving environment where every moment is a struggle for survival. Our presence there is fleeting. A few days, a few years, a nothing on the geological timescale. On the other hand, there is the unimaginable permanence of the legacy left by that fleeting presence. The footprints of the Apollo astronauts will remain there for millions of years until the next major impact. The U-22 rover, when it one day falls silent, will stand like a monument on that plane for billions of years. The lower part of the Chang'e 6 lander is the first permanent artifact of human history on the far side. Our presence is temporary, but our trace is almost eternal. The tragic side of this is how insignificant our physical presence is. We are not natives of that rocky world. We need the armor of technology to survive there. We don't belong there, and this is a painful reminder of how much of the universe is closed to us. We are fragile creatures, dependent on the delicate biosphere of our own small blue planet. But within this fragility lies that beautiful but again. Our physical presence may be temporary, but our ideas, our knowledge, the symbols of our curiosity can be permanent. That footprint is not just a mark, it is a statement that says, "We were here." That abandoned lander is not just a pile of metal. It is proof that says, "We tried to understand." We leave not just physical traces in the universe, but also traces of meaning, and that meaning is far more durable than metal or dust. You too are a temporary presence in this world. But the impact you create throughout your life, the knowledge you share, the hearts you touch, form the legacy that will live on after you. You too are leaving a trace beyond your physical existence. And this act of leaving a trace confronts us with a final contrast, the contrast of purity and interaction. The far side of the moon was a pristine, untouched archive for billions of years, a perfect radio silence, an untouched geological record. It was a book written by the universe itself, but read by no one. On the other hand, there is us. To read that book, we must touch its pages, analyze its ink, and in the process, inevitably change it. To listen to that silence, we must break it with the signals of our own relay satellites. To land on that untouched surface, we must pollute it with the exhaust of our rocket engines. To understand, we must touch. And everything we touch, we change. This is the most fundamental paradox of exploration. To understand the pure, we must disturb its purity. The sad part of this is the loss of innocence. Once touched, that surface will never be the same again. Once listened to, that absolute silence will no longer be absolute. We, as observers, inevitably affect the system we observe. This is an irreversible change, and this is a responsibility and perhaps a certain grief that comes with discovery. But within this inevitable change lies the most fundamental and beautiful dynamic of consciousness. Without interaction, there is no understanding. Without risk, there is no exploration. To stand back in fear of contamination is to remain ignorant forever. To touch that surface is to enter into a dialogue with the universe. To send that signal is to ask a question of the silence. The traces we leave are not wounds, but evidence of a conversation. And this conversation is the only path to knowledge, to growth, and ultimately, to wisdom. You know from your own life that you can't learn anything by watching from a distance. Building a relationship, playing an instrument, writing a book, they all require interaction. They all disturb the state of pure potential and turn it into something real, something tangible. And this is the very act of creation. We are not just the readers of the universe, but also its co-authors. But where does this lead us? But this brings us to perhaps the most challenging and most important contrast of this entire journey, the contrast of competition and collaboration. On one hand, the moon's south pole in the 2020s has become a new gold rush territory. NASA's Artemis program and China's plans for an international lunar research station are progressing as parallel efforts by two major geopolitical powers targeting the same resources, the same strategic locations. Laws like the Wolf Amendment, passed in 2011, which prohibits NASA from direct bilateral cooperation with China, make this division even sharper. This is a reflection of one of the oldest and most stubborn aspects of human nature: competition, tribalism, and mistrust. On the other hand, there is the universal spirit of collaboration inherent in the nature of science itself. The data from Chang'e 4 was published openly and analyzed without restriction by American researchers. The Chang'e 6 mission carried international scientific instruments from France, Italy, Sweden, and Pakistan. Science knows no passport. The laws of the universe do not respect national borders, and the greatest discoveries often arise from the broadest collaboration. How can this be? How is it that when we need to work together for our greatest goal, we also bring our oldest divisions with us? The tragic side of this is the potential for this competition to slow progress and waste resources. Building two separate programs, two separate infrastructures, two separate communication systems is far more expensive and less efficient than a single, unified effort. This could potentially delay scientific discoveries and make it harder for humanity to establish a sustainable presence on the moon. It is the reflection of our divisions on Earth projected onto the sky, and it could be a sad proof of how we can sabotage even our greatest opportunity with our oldest weaknesses if we are not careful. But within this competition, there is also an unexpected and beautiful dynamic at work, because healthy competition can also be a powerful incentive. The original space race of the 1960s was a product of the Cold War, but it also triggered an incredible wave of technological and scientific breakthroughs. A similar situation may be happening today. The fact that both America and China have ambitious plans for the moon forces both sides to be faster, smarter, and more innovative. This competition makes it easier for both programs to find political and financial support. Perhaps ironically, our division could push us further than we could go alone. You know that sometimes you deliver your best performance when you have a rival pushing you. It is a tension that pushes us to be better. And perhaps the path to the moon runs not through pure cooperation, nor through pure competition. Perhaps the path runs through a complex, and sometimes uncomfortable, dance between the two. This brings us to a final philosophical layer, the contrast of dreams and reality. On one hand, there is the romantic, poetic dream of the moon goddess Chang'e and her faithful companion, the jade rabbit Yutu from Chinese mythology. The very names of the mission remind us of the magical, untouchable place the moon holds in the human imagination. It is that silvery disk in the sky that inspires poets, artists, and lovers. On the other hand, there is the brutal, unforgiving reality of the moon. Temperatures that drop to minus 190 degrees Celsius. Electronics that would freeze without radioisotope heater units. A sharp, abrasive dust. And an absolute, indifferent vacuum. This is a place where dreams die, where only engineering and physics survive. How can this be? How can the object of our most poetic dreams also be the embodiment of the most brutal reality? The sad part of this contrast is that some of the magic is lost when we step into that world. When we reduce the moon to a set of equations, a table of mineralogy, an engineering problem, we lose some of its mysterious aura. Looking closely sometimes kills the romance. Just like when you learn a magician's secret, some of the magic of the show is lost. But in this inevitable confrontation, a much deeper and much more lasting beauty is born. Because reality is far richer, far more complex, and far more surprising than imagination could ever offer. No poet could have dreamed of the billion-year-old layers lying beneath the surface. No mythology could have predicted the spectral signature of olivine and pyroxene, and no artist could have painted the whisper of the Dark Ages signal in that silence. Reality does not destroy our imagination. It feeds it. It gives it a new foundation on which to build new and previously impossible dreams. We no longer just look at the moon, we understand it, and that understanding allows us to form a bond stronger than even the most poetic dream. You have experienced this in your own life. To truly love someone means to know their flaws, their complexities, and their reality. This may destroy the initial idealized dream, but in its place, it builds a much deeper, much more real, and much more lasting love. We fell in love with the moon. But now, we are truly starting to know it. And at the end of this journey, we now know the far side of the moon is not just a geographical location. It is a mirror that shows us who we are, where we come from, and where we might go. In that silence, we heard the echoes of our own questions. In those ancient rocks, we read the lost history of our own planet. And in the tracks of that lonely rover, we saw the proof of our own curiosity and resilience. This was a story of time and scale, of destruction and creation, of loneliness and connection, of competition and cooperation, of dreams and reality. But in the end, this is not just the moon's story. This is our story. And this story is not over yet, because every answer gives birth to a new question, and every destination is the beginning of a new journey. The far side of the moon has given us one of its secrets. But now, we are just beginning to understand what that secret tells us and what we will do with that knowledge. In this video, we searched for a single truth on the far side of the moon, but I didn't tell you something. What if the reality we're looking for is just one of infinite possibilities? The laws of physics allow for the existence of not just our universe, but an infinite number of parallel universes. Infinite U's, infinite choices. On our next journey, we dive into the many worlds theory. Are you ready to meet your infinite selves?